Welcome back, everyone. So in this part of the presentation, we'll be discussing outcomes, exposure, and risk as they pertain to environmental toxicology. So there are a lot of potential negative outcomes associated with exposure to toxic substances, ranging from relatively minor responses like coughing or sneezing to very serious responses like cancers or birth defects. It's possible that some chemical and physical agents can alter DNA through mutations, which can happen in either body cells or reproductive cells. Those occurring in body cells may kill the cells or lead to cancer. And non-lethal changes in reproductive cells can be passed on to one's offsprings. Cancer is related to uncontrolled cell growth. Tumor cells typically develop in rapidly developing cells, such as those in the skin, and are often spread to other parts of the body. There are hundreds of types of cancers, many of which behave differently, which complicates efforts to find cures. Cancers can be caused by chemical, physical, and biological agents. The chemicals that cause cancer, called carcinogens, generally require repeated exposures over many years. And most carcinogens react with the growth control genes of cells, causing mutations that lead to the cancer. Birth defects include structural and functional defects in newborns, which may be caused by physical, biological, or chemical agents called teratogens. Impacts of exposure to teratogens may be different depending on the stage of embryonic development, which we'll see on the next slide. The effects of these chemicals may also vary, with some affecting specific organ systems and others affecting multiple systems. You can see a list of some of the known and suspected teratogens in the table. This graph shows teratogenesis with respect to stages of embryonic development. As you can see, the impact on the embryo is dependent not only on the chemical, but on the stage of development, and some stages are much more susceptible to negative outcomes. One of the things that can impact the effect of a toxic substance is the chemical mixture. Here are some examples and definitions. Additive means that the combination of two chemicals produce an effect that's equal to their individual effects added together. Synergism indicates that the combined effect of exposure to two or more chemicals is greater than the sum of their individual effects. So when two chemicals are together, the impact is greater than each one separately. Potentiation happens when one chemical is not toxic, causes another chemical to become more toxic. And finally, antagonism means two chemicals administered together interfere with each other's actions, or one interferes with the action of the other. Another element to the impact of exposures is the duration of exposure. Basically, how long are you exposed for? These are a few terms that we need to know. Acute exposure, which is usually a single exposure for less than 24 hours. Subacute exposure is when the exposure is for a month or less. Subchronic exposure, which is exposure for 1 to 3 months, and chronic exposure, which is exposure for more than 3 months. As you can probably guess, you can handle an acute exposure of higher concentrations of a toxicant more easily than you could for a chronic exposure, since you'll be exposed to it for a shorter time and as such get overall a lower dose. There are a number of ways that these exposures can impact health. There are local effects, which are characterized by damage at the site where a chemical first comes into contact with the body. Systemic effects suggest a generalized distribution of the chemical throughout the body by the bloodstream to internal organs. And target organ effects are when the chemical confines its effect to specific organs. Latency refers to the time period between initial exposure and a measurable response. This can range from a few seconds in the case of acutely toxic agents to several decades, like some carcinogenic agents. Typically, when there's a long latency time, public health studies have a much harder time showing not only causality, but also associations, since there are likely to be so many other potentially unrelated exposures between the exposure to the original agent and the outcome. This takes us to risk assessment. Risk assessment provides an estimation of the likelihood of adverse effects that may result from exposure to a hazard or from the absence of beneficial influences. These risks must be understood and quantified in order to create socially, economically, and environmentally acceptable policies. Specifically, risk assessment helps us identify risks, determine the probability of their occurrence, and assess the potential severity of the effects, whether they're economic, health, social, or ecological. Risk assessment has a number of major steps, which include hazard identification, dose response assessment, exposure assessment, and risk characterization. So what is a hazard as opposed to a risk? A hazard is the inherent capability of an agent or a situation to have an adverse effect. So it is the innate ability for something to hurt you. For instance, botulism toxin, which has a very high toxicity, is a hazard. As such, hazard identification examines the evidence that associates exposure to an agent with its toxicity and produces a qualitative judgment about the strength of that evidence. This basically means that it identifies a substance as a hazard. The dose-response assessment, which we've already discussed, measures the association between the amount of exposure and the occurrence of unwanted health effects. So exposure assessment is the procedure that identifies populations exposed to the toxicant, describes their composition and size, and examines the routes, magnitudes, frequencies, and durations of such exposures. So exposure assessment tries to answer the following questions. Who or what is exposed? For instance, specific populations, aquatic ecosystems, the upper atmosphere. What is the route of exposure? Does the exposure occur through breathing air, drinking water, skin contact, or other routes? How much exposure occurs? And how often and for how long does exposure occur? That is, what is the frequency and duration of exposure? There are two main steps in exposure assessment. Estimation of the pollutant concentration, which often is done through modeling, monitoring, or simply locating the source, and estimation of exposure of the target to the pollutant. This is often done with stationary monitoring, personal monitoring, proximity assessment, and other modeling techniques. These next few slides show some ways that exposure can be estimated. In this case, we're looking at PM2.5, which are small particles that are often airborne and associated with a number of health outcomes, including respiratory and cardiovascular disease. This first slide shows EPA monitors that were in New York City, or at least they were back in 2002. The larger dots represent higher monitored concentrations of PM2.5. There appears to be some sort of geographical trend in the concentrations, but it may be a little hard to say for sure due to the small number of sampling sites and the way those sites are distributed across the city. Also, these sites tend to be on top of buildings, so they may not reflect the air we're actually breathing. However, these monitors can be a good source of data that you can use to estimate exposure. This shows remotely sensed data, meaning satellite data, from the Moderate Resolution Imaging Spectroradiometer, or MODIS. The darker areas have higher concentrations of particles. However, this also has some limitations in that the resolution is pretty low, and the measurements come from the entire air column from the Earth to the satellite, so they may not represent what humans are really being exposed to. This slide is showing the major stationary sources of PM2.5 pollution in the city, again from back in 2002. The red points represent the actual stacks of the facilities that are emitting the pollution. This is different from the MODIS and EPA data from before in that it focuses on specific sources of pollution rather than ambient levels. With this stack data, we can do a simple analysis to estimate who is most impacted by those sources of pollution. This slide shows simple proximity buffers, which make the assumption that if you live close to a source, you're more impacted by it. This slide shows the beginning of a method called land use regression, where you analyze land uses around monitors to try and calibrate what is basically a regression equation. You then apply that parameterized equation to areas in the city that do not have monitors in order to estimate the concentrations in those locations. This is a way to mitigate some of the shortcomings we saw with the EPA monitors in the earlier slide. And these are the outputs. The map at the bottom right shows the estimated PM2.5 concentrations based on land use regression. You can also use something called dispersion modeling. This map again shows the sources of major PM2.5 emissions with larger sized dots representing more emissions. Air dispersion model uses a tremendous amount of data, including wind speed, humidity, and temperature in both the upper and lower atmospheres, temperature and velocity of the gas being emitted, diameter and height of the stack itself, and even topography on the ground and impact of surrounding buildings. All of these data and more basically model where the PM2.5 would go, given all those conditions. And this is the output of that particular air dispersion modeling effort. And if you can still remember back to the slide that had elements of risk assessment, this is finally the risk characterization. So, risk characterization develops estimates of the number of excess unwarranted health events expected at different time intervals at each level of exposure to a hazard, meaning exposure to toxic substances. Risk management usually follows risk characterization and seeks to control exposures to hazards. It's important to note that risk can come from natural events or human activities, but we also have to remember that human activities can influence natural hazards and vice versa. So this risk characterization can be really difficult because so little is known about many of the chemicals we come in contact with, as well as their interactions and our potential exposures. Also, much of the toxicological work is done on laboratory animals, so the findings may not apply to humans. To further complicate things, the acceptability of different forms of risk, known as risk acceptability, is not very straightforward and can be driven by perceptions. For instance, the graph below shows acceptability of risk on the vertical axis and perceived benefit on the horizontal axis. The higher the perceived benefit, the greater the risk we're typically willing to accept. However, if we are exposed voluntarily or involuntarily, can impact how acceptable it is. This is shown by the blue and red lines. As an example, cars undoubtedly are a hazard in that they emit various toxic substances through their exhausts. But because many of us perceive benefits to cars driving around the city, we're more likely to accept this risk. On top of that, if you are voluntarily exposed, in other words, if you own a car and get exposed by your own exhaust, you will be more likely to be okay with higher risk when compared to someone who happens to live right near a major roadway who maybe doesn't own a car and as such doesn't get exposed to the exhaust voluntarily. So there are a number of ways to determine if the risks posed by a technology or activity are acceptable. The most common method is a cost-benefit analysis, which weighs the costs, in other words, the bad things, against the benefits, in other words, the good things. Sustainable development strategies minimize social, economic, and environmental costs and maximize the benefits, or that's the goal anyway. So risk assessment is designed to facilitate decision-making by ensuring that the risk we perceive to be posed by something is equal to the actual risk that there is. This is to a degree led by the values, culture, ideals, and character of the stakeholders in the process. But often these values can be a bit narrow or short-sighted with respect to both space and time. So it's important, although rare, to have a long-range view that encompasses the entire planet. And this is important in terms of sustainability particularly. I think this graphic does a really good job of showing the role of perception and associated values in the risk assessment process. The top yellow box shows the actual risk. The left column of boxes shows the series of events that may happen if the perceived risk is greater than the actual risk. Basically, you end up with bad policy that leads to overprotection from the risk. An example of this may be the perceived risk of new immigrants carrying infectious disease. There are some policies or attempts at policies that use this as a rationale for overprotection. This is not to say that infectious disease is not something that needs to be thought about, but rather that the risk should be quantified rationally. The second column shows what may happen if the perception matches the actual risk. In this case, the policies would be well designed and the level of protection appropriate. The last column on the right shows what may happen if the perception is lower than the actual risk. This can lead to policies being created or not created that underprotect. One example of this may be controls of greenhouse gas emissions or climate change mitigation. If the risk is not perceived as serious, then appropriate policies won't be designed, resulting in a lack of action. So that's the end of this presentation. As always, please post questions or comments to Blackboard or email me anytime. Thanks very much.